Okay, hello everyone. Thank you so much for joining us. So my name is Mais Bediazi and I will be hosting the webinar today. I was studying at ENAC as an engineering track from 2016 to 2019. And today I work at the European Space Agency as a service implementation engineer for the Galileo second generation. And I will be your host for today. So just a few words about ENAC alumni. It's also the organization of graduates for ENAC. I think it has now more than 28,000 members around the globe. And correct me instead if I'm wrong. And the purpose is to maintain and develop relationships within graduates, but also to assist members in their job searches and transitions, and to promote personal development for our alumni. And what about us, the Space Think Tank? Well, actually, I co-founded the Space Think Tank with Nicolas Soulard and other fellow classmates who might be with us today, to basically tell graduates or future graduates that after ENAC, we can also work in space. We don't necessarily all work in civil aviation. And so if you are curious or just passionate about the topic of space, feel free to join us. We try to organize webinars like this, let's say up to 3 times a year. And also we do after work events. And maybe in the future, we would like to do full day events or workshops. So if you have any ideas also on your side, feel free to contact us. I will put my email in the chat later on. So now today we have a webinar on Galileo for civil aviation. So I'm happy to have as guests my dear colleagues Santiago Diaz and Eric Bouton here with us. They both hold a PhD. Santiago on his side has been in charge of the safety of life service since 2021 at ESA. He has a Bachelor and Master of Science at the University of Sevilla, and a Master's in Mechanical and Aerospace Engineering from the Illinois Institute of Technology in the US. And he holds his PhD in electrical engineering from the RWTH Aachen University in Germany. From 2013 to 2018, he worked as a research associate at DLR, which is the German aerospace agency. And from 2018 to 2021, he worked at Airbus Defence and Space as a safety of life engineer. You can say hello, Santi. So this is Santiago. And then on the other hand, we have Eric. So Eric is in charge of the search and rescue and emergency warning services at ESA. He has over 15 years of experience in telecommunications and mainly in the field of wireless systems. Before working at ESA, he worked in the mobile telecoms industry and mainly specializing in 3G, 5G standardization and intellectual property. He obtained his bachelor's and master's degree in electrical engineering from the Federal University of Pernambuco in Brazil. Sorry for the pronunciation. And before pursuing a PhD at Telecom Paris. So briefly to introduce the webinar, Eric and Santiago will be talking about the respective services they oversee at ESA and how these services support civil aviation today, and will also continue to support civil aviation in the future. A quick background on Galileo, I guess you are familiar with it, but just a few words. The first Galileo satellite was GOVA was launched in 2005, and the first satellite of the operational system was launched in October 2011. To date, with 28 satellites in orbit, Galileo provides meter-level accuracy to more than 4 billion users around the globe. There are currently 10 further Galileo satellites due to be launched, and after that, the first Galileo second generation satellites bringing new capabilities will be launched in the coming years. So all smartphones sold in the European single market today are now guaranteed Galileo enabled. And in addition, Galileo is making a difference in a large variety of domains like rail, maritime, agriculture, financial timing services, rescue operations, and of course, civil aviation. That's why we're here today. So the webinar will be organized as follows. We will first have the presentation from Eric on search and rescue and for civil aviation for about 15 to 20 minutes. Then Santiago will also give his own presentation on safety of life and for civil aviation. After that, we will have a short panel-style exchange with Eric and Santiago, and we will leave the rest of the time for the questions from you, from the audience. So throughout the webinar, feel free to drop your questions on the chat. You can also put your name and affiliation before the question, and I will make sure to collect all of them and ask them to our guests at the end of the webinar. So thank you again, for joining. Please also make sure if you're not talking that you stay on mute so everyone can enjoy the webinar today. And I will now give the floor to Eric to talk about search and rescue and its support to civil aviation.
All righty. Thank you, my Lisa. Can you hear me? Okay. Let
Yes, yes.
me. All righty. Let me try to share my screen here. See if I manage. Give me 1 second. Share screen. Second screen. Share. All right. I guess what you can see is likely the
Yes, it's okay.
title.
Mm-mm.
Yeah,
You see
yeah,
it? You see it
yes,
correctly? All right.
Yes.
yeah. All good.
Alrighty. So, okay. So let's thank you, Miley, for the very kind introduction. I will try to keep it to 20 minutes, but I don't really guarantee it. But I will do my best. So, hello, everyone. My name is Eric. As Miley said, it's really a pleasure to be here today to present a part of the activities of the EU's Galileo program, which focuses on search and rescue. Um, Perhaps you know this already, or maybe this might surprise you, but search and rescue is one of the services provided by the Galileo constellation. And what is SAR Galileo? Well, it is a contribution that the program, under the Galileo program, provides to search and rescue operations around the world. And what we're going to do is spend a little bit of time to understand the general points of this very cool system, and also spend a little bit of time on trying to understand how it provides support to the aviation industry. Okay, so as I mentioned, um, Galileo contributes to a global initiative on search and rescue, which is the International COSPAS SARSAT program. You might have heard of it. And more specifically, Galileo contributes to Cospasarsat in medium Earth orbit. As you know, Galileo is a constellation on the MEO orbit. So it's called MEOSAR. So what I'm going to do in the presentation is to start with a little bit of context and general description of the Cospasarsat program, because I think it's always important to know where we're coming from to understand where we are and actually where we're going to. Then I'll speak a little bit about the first days of Cospasarsat and what the system looked like at the time, and then move on to the current system in MEO. I'll talk a little bit about the infrastructure and the bespoke functionalities that the Galileo program provides to the Cospasarsat MEOSAR system, both in terms of space segment and ground segment. I'll show you a couple of examples of the system in action and give you some pointers to how SAR Galileo and Cospasarsat in general support the aviation industry. Also, today, we're in a very interesting moment in the project. We're transitioning from the first generation to the second generation of Galileo. And because of this, we are developing a number of new services to support emergency operations based on the existing infrastructure or some modification of the existing infrastructure. And at the end of the presentation, I'll talk a little bit about these new services and focus on one particular service that is of interest to the aviation sector. Okay, so to start, a little bit of background on the International COSPAS-SARSAT program, which is a satellite-based search and rescue detection and information distribution system that is dedicated to detection and location of emergency radio beacons activated by other aircrafts or ships or people in distress in general. The program was founded, as you can see in the picture on the left, in 1979 by 4 countries, these being Canada, France, the United States, and at the time the Soviet Union. And the first rescue supported by the program was in Canada. You can see a picture here and took place in 1982. So since then, the program has been offering search and rescue services or supporting search and rescue operations, and of course has evolved tremendously since its first day. Today, we have 31. We have, of course, 4 parties, which are the founders, and we have 31 states participating in the program, providing land support segments and also space segment assets. Okay, so initially, the COSPAS-SARSAT system search and rescue system was based on satellites which were orbiting the Earth in low Earth orbit, the so-called LEO SAR system, which were supplemented by several satellites in geostationary orbit. But like every system, this choice has advantages and disadvantages, as you can see here on the slides. For example, satellites in low Earth orbit have the ability to detect radio beacons transmitting at low power, but precisely because they are in low Earth orbit, the visibility of the satellite uh, into the Earth is kind of small, which results in lots of or potential delays in detecting alerts. And conversely, satellites in geostationary orbits make up for these shortcomings because they're able to see globally 1/3 of the Earth's surface. But because of their stationary orbit with respect to Earth, they cannot they cannot enable. They only enable localization, and also they do not cover the pulse. They only enable detection. So the complementation of the two gives the original or the initial deployment with some caveats, let's say. And then in the early 2000s, the COSPA-SARSAT working groups, it became apparent within the COSPA-SARSAT standardization program, it became evident that a system based on satellites in MEO could compensate for several of the shortcomings of the LEOSAR and GEOSAR systems. And because of the strong synergy with GNSS systems provided around the world already, this gave the final push, let's put it like that, to the program to decide to transition towards a SAR system in medium Earth orbit. Um, and so the transition of the MEOSAR system represents really a major evolution um, of the overall program. It allows really for a series of um, performance improvements with respect to the existing ones, LEOSAR and GEOSAR, as you can see here on the slides. So first, you are able to have near instantaneous worldwide detection, improve location accuracy, and you have, because of the geometry, a significantly reduced effect and the redundancy you have around effect of terrain and wreckage or sea state obstructions. Um, on top of this, the program has been able to implement acknowledgement of reception of localization alerts. This has been enabled by Galileo. I'll talk a little bit about this in uh, in the further slides. And it has been developed with not only sort of to be put in a future-proof mode, but also with interoperability in mind. So all the four existing GNSS constellations provide a contribution to the system, and they're all um, interoperable. Um, what's important to say today is that the LEO and GEO services continue to be provided. So the MEO system provides a complement to them, but because of the large number of MEO satellites that we have, it is today seen as the main provider of the COSPA-SARSAT system. So just before moving on to the details of the system, here are some facts which help to support the usefulness of COSPA-SARSAT. Just in 2022, there are more than 1,000 events that were supported by COSPA-SARSAT, and where more than 3,000 people were rescued. The number of events in total has been proven to go beyond 50,000 rescues worldwide since it started in 1982. And here on the right, you see where most of alerts have been detected, and is of course highly correlated with the countries that actually are participating actively in the system. So for sure, there is potential to support um, even more SAR events. So let's have a little bit of a look of the high-level concept behind COSPA-SARSAT, and in particular SAR Galileo. As I had initially tried to illustrate this with a diagram myself, but I'm very bad at graphic design, so I am relying here on this very nice infographic that has been provided by our external communication colleagues. And here, if we start at number one, you can see on the left side, let me see if I can point here with a laser pointer here. You can see a distress event starting. A beacon has been activated by, say, a ship, either manually or automatically. This is transmitted over the air and is relayed by all the MEOSAR satellites. There are more than 40 around the world orbiting and providing constant coverage of the whole globe. These are received by local user terminals that support MEO operations, so medium Earth orbit operations. So these are called MEOLATs. And the message is then decoded. It's received by several from several satellites at the MEOLAT, which then trilaterate this distress alerts, located within certain with a certain accuracy, and then forward this to the mission control center, which is in charge of sort of coordinating the confirming that the alert is a real alert and forwarding the message to the appropriate rescue coordination centers, which then launch the emergency responses. In parallel, what we can see here is a small line which sends the alert as well to the Galileo system, which then uses the Galileo satellites to provide an acknowledgement back to um, to the users in distress to tell them that their alert has been well received, well detected, and located. So this is quite an important feature of COSPASARSAT, in particular of Galileo, because it is well known that receiving an acknowledgement that your signal has been heard by somebody is really a boost to morale and really improves the will to live. Um, so this is something quite interesting. Um, so now that we have a rough understanding, I'm sorry for rushing this a little bit, but the time is constrained. But so now that we have a rough understanding of how the MEOSAR system works, let's look at the Galileo contribution to the system. The Galileo contribution here, as we can see, I tried to lay it out in a few bullets. It provides the COSPA-SARSAT program in kind with SAR payloads on board Galileo satellites. All but two Galileo satellites in orbit have SAR transponders. A ground segment for the forward link, so MEOLATs and reference beacons and things that I will talk about in the next couple of slides, and ground segment as well for the return link. Two services are provided: the alert service, which detects and locates users in distress, and the acknowledgement service that acknowledges to the users in distress that their alert has been heard. The coverage is, of course, worldwide and is free of charge, apart from the purchase of a beacon, which is for a personal beacon, roughly around 200-300 euros, so quite cheap. So let's have a look at the Galileo infrastructure a little bit in more details. I'll go a little bit fast here so that we can focus on other things. But still, I wanted to show you a couple of nice pictures. So let's start with the SAR Galileo space segment. And the Galileo program provides nominally 24 payloads in orbit with SAR transponders on them. This number obviously varies up and down depending a little bit on launch schedule, the satellites which need to be replenished. But nominally, we have 24 satellites plus 6 spares, all of them with SAR payloads. And here on the right side, we can see a little bit of a more detailed view of the Galileo satellites and the antennas facing the Earth's surface, where the arrows can give us an indication of the path followed by the alert signals. So here, they are received, the SAR beacons alerts are received by this conjunction of 6 helices, and then are processed roughly, are converted in frequency, and then relayed back on Earth by this antenna here in the center. And then for the return link and the acknowledgement message to the users, this is uplinked to the satellite here, received here, and then forwarded back to the users using the main navigation antenna. And here on the left, we see a nice picture of the first two Galileo satellites with SAR payloads, which were launched in October 12, 2012. So it's always nice to see a rocket, no? um, then on ground, um, we have several facilities scattered around the world, the main being the three ground stations which are placed strategically around at the edges of the European continent. Here we have a Miolot in Larnaca in Cyprus, another one in Spitsbergen in Norway, and another one in Maspalomas, covering, if you look at the triangle, it covers most of the I mean, it covers all of the continental continental Europe, but it actually goes much further. On top of this, there's a number of other assets which we are continuously putting in place to improve the service. So we have here in La Réunion, we have a new Miolot, which has been commissioned last year, and it covers a large hole that the COSPA-SARSAT program had in the Indian Ocean. We also have reference beacons here and all over the place to be able to monitor the performance of the Galileo system and see if everything is operating correctly. In Toulouse, we have the main operation where most operations are managed, and there is also the RLSP, which I'm going to talk to you about in a little bit. So the RLSP being the Return Link Service Provider, which is the entity in charge of making the message that is going to go back to and uplinked into space and going to go back um, to the user in distress. So that was it for the forward link. Now, what is the return link? So the return link, very quickly, um, as I mentioned, is implemented by Galileo via this entity called the RLSP, or the return link service provider. Is part of the SAR Galileo ground segment, but is not part of COSPA-SARSAT. Rather, it is connected to COSPA-SARSAT via this mission control center, which is part of COSPA-SARSAT. In practice, when an alert from a beacon which is compatible with the return link is detected and located, then the appropriate mission control center forwards this to the French mission control center, which in turn is connected to the RLSP, and then which puts the message together, sends it to the Galileo core infrastructure, which then relays it back, as you can see here, to the user in distress. And the RLSP, the RLM, or the RLS, actually, the return link service, is the basis of a number of new services which we are developing. So today we provide what we call the acknowledgement service, but there's a number of other services which we are developing and which will soon be put in place. One of which is very relevant to the aviation sector, is the beacon command service, where you are able to activate a beacon remotely if, for example, a vessel goes missing. And I'm sure you can already think about a couple of examples where this could be relevant. There's other services which I'm not going to dwell too much upon, but because of the constraining time, but we also are able to, for example, share information about a possible beacon in distress in the vicinity so that others um, can assist in the emergency. Or we have also implemented a way to have rough communication by exchange of very sort of coarse messages with the users. So these are a number of things that we are putting into place, and if you can always contact me if you're interested to know a little bit more. But just before we go into the say contribution to civil aviation, I would like to show you a small video of what you can expect from well, when you activate a beacon. And in fact, I have the exact same beacon which is shown here in my hand. So this is a personal beacon. You can see it's very small. I hope you can all see it. And here it has been activated as a test, and this is it's very quick. It's a couple of seconds. So you activate your beacon. The antenna here on the left is on the right, sorry, is deployed, and then very quickly you will start seeing this blue light, which shows you that the distress has been received, detected, located, and um, and that the acknowledgement is yeah, here shown in the picture. So this is more or less how it operates. It's quite simple as a concept of operations, let's say. So I am, because I'm a little bit late already, I am going to skip the slides on demonstrations. I wanted to show you a little bit about, so I'll go very briefly. We have already put a number of demos and in place to raise awareness and to test the system. So the first of which was in Belgium, where we put a live raft with somebody on here you can see activating a personal beacon like this, and simulated a whole operation where the person would receive a return link and be reassured that they are that they have been heard. And recently we also tested the performance of the system in Svalbard, at the very north of Europe, to see the performance close to the poles, where a performance can sometimes be a challenge. And we can see that at least the return link provided very good performance within 2 minutes, and the detection and location of the users within 730 meters, which is quite an impressive um, feat. Then I wanted to show you a little bit about a real distress, which happened in 2020 in the Vendée Globe, where the person was rescued thanks to the COSPA-SARSAT and system, and the assistance, or a real life demonstration of this distress position sharing, where a fellow competitor, which was around the person in distress, received the alert, this time manually, but was able to turn their ship around and help with the rescue of this sailor in distress. But let's spend a little bit of time just to what's interesting, I think, for the crowd here, um, is um, is that is the support of COSPA SARSAT and Galileo in particular to aviation. So I wanted to spend a little bit of time on this. I am not an expert on civil aviation, so please bear with me if I am a little bit imprecise in the terminology I use. Um, but what I wanted to tell you is that today, and since a little bit of time, most civil aircraft must carry what are called ELTs, so emergency locator transmitters, which are a big version of this. And they are COSPA SARSAT compliant beacons. Of course, the thing with COSPA SARSAT beacons is that they're meant to be activated after the emergency has occurred. In aircraft, the problem is, of course, ELTs can be destroyed in a crash and then fail to activate altogether. And on top, a number of tragic events, like the crash of the Rio-Paris Air France flight, or the disappearance of the Malaysian Airlines Flight 370, in recent years have sort of eroded the public's trust in international civil aviation. And this led to a number of rapid actions by ICAO, which in turn result in the development and of this Global Aeronautical Distress and Safety System, or the GATS, and the adoption of GATS-related aircraft traffic initiatives globally. And one such initiative is the development of a distress tracking ELT, or the so-called ELT-DTs, by COSPA SARSAT. So what is GATS? I will try to give you really the main lines of it, because I'm sure most of you are more of an expert than I am in this. But it has four main objectives, which ensure first, timely detection and timely detection of aircrafts in distress, tracking of the aircraft in distress, and accurate location at the end of flight, efficient and effective SAR operations, and timely retrieval of flight recorded data. So to support these objectives, three high-level functions have been identified. So aircraft tracking, for normal operations, which reports the aircraft position every 15 minutes. Autonomous distress tracking, which identifies possible abnormal behaviors of the aircraft and adapts reporting times to support a possible distress situation, and post-flight location and recovery, which puts in place a number of measures to improve SAR operations and retrieval of functional flight data recorders. So you can think of putting two data recorders in place, or recording in the cockpit with extended um, recorded capabilities for more than what a flight would normally last. Now, several ICAO documents are applicable to this GATS implementation. Um, I have it in some notes in the presentation, which I think will be shared with you afterwards. But it provides sort of, for example, ICAO Annex 6 or the IAM-SAR manual version 2022, and other documents as well. What all these documents do is that they are applicable for the implementation, but they do not specify any particular technology. And therefore, COSPA-SARSAT has decided to support GATS, and in particular, the autonomous distress tracking function of it, by specifying a specific kind of ELT, the ELT-DT, which I mentioned a little bit before. So this ELT-DT implements autonomous distress tracking, and unlike normal ELT, automatic and fixed ELTs, these ELT-DTs are tightly connected to the avionics system of the aircraft and activate automatically while the plane is still flying upon detection of a potential distress condition that can go from, say, unusual attitude or unusual speed, an imminent collision with terrain, or a total loss of thrust. And what it does, these ELT-DTs have a unique transmission characteristic where the transmission schedule is adapted depending on what kind of potential, say, distress situations we're in. They don't transmit for 24 hours. They only transmit for 370 minutes at that during this potential alert, but they can transmit up to bursts every 5 seconds. And well, as you can see here in the slides, there's quite a specific schedule which optimizes the automatic distress tracking system and tailors to the specific distress condition the aircraft is in. So now going back to SAR Galileo, um, I will just tell you a little bit. So these are all um, the new service that we're looking into, but I will only focus on the beacon command service because I think this is what is of most interest to the crowd here. The beacon command service for remote activation and deactivation of beacons has already a standard published by EUROK, and it's the service we're developing, which is in its most advanced state. So I will only focus on here. Here is the sort of the very high level concept of operations. Is quite easy to understand. The difference here is that instead of having a distress started by somebody in distress, the sort of distress in a sense or a situation where the beacon starts to emit is initiated by, say, air traffic control, which has lost the aircraft. So here you can see that there is an external user which is authorized. It sends a request to the return link service provider, which is connected to Galileo, and then asks for a dissemination of an RLM, a return link message, which will be then disseminated to the potential aircraft, say here MH370, which will be activated remotely, therefore helping the actual distress situation to start. And then it follows the normal COSPA-SARSAT route. So we are thinking about a number of services that that can be implemented via the return link, and this is one of them. So just to conclude and not to go over half an hour, to wrap it up, what I've been talking about is a search and rescue service of Galileo. What we do is taking the search word out of search and rescue, because it reduces the time for detection really to minutes, and has a very reliable performance for location of the emergency. So hopefully there isn't much searching, and the efforts can be really concentrated on the rescue part of the operation. Then we also have been talking about the acknowledgement service, the return link service, which supports the rescue part of the search and rescue operation by providing reassurance to the persons in distress. As I said, we have heard this many times over and over, that the importance of having some confidence that rescue is on its way, that which helps to maintain the spirit and the will to survive. And then I have talked a little bit about the very little bit about the new services that we are preparing, including one which is directly supporting the aviation industry, which is the remote beacon activation service. So that's it. Thank you very much for your attention. If there are any questions, I'm happy to take them. Either I suppose that I'll give the floor now to Santi, and then we'll take questions afterwards. That's it for me. Thanks.
Thank you so much, Eric. Thank you. That was very
Thank you.
insightful. Thank you for the presentation. And just what you were
Thank you.
mentioning before, remote beacon activation, I think there was a test conducted with Iberia and Air France, no, in 2019, I believe, the first test of this remote beacon activation.
It is possible, but
Yeah.
I don't think it has been, at least it has not been done via ESA. It is either something that
Yes.
has been done
Yeah.
via the European Commission directly, or
Via USPA, I
there.
think. Yeah.
Okay, then yeah,
Yeah.
it is very, very well possible. Yes.
Okay. Thank you. Thank you
Alrighty.
very much.
So
Very interesting. Thank you. So yes, indeed,
let
I will now give the floor to Santiago
okay,
to
let me
talk
stop
about.
sharing.
Yeah. Thank you
Uh,
so much.
Excuse
Yes.
me, Maëlys, there is a question from Mohamed in the chat.
Yeah.
You want-
I think should we keep them for the end, or you want them? You want us to ask it now, Estelle? What do you think?
well,
Was thinking of Kimi.
as you want.
Okay, for sure. Maybe we might as well because it's related to your presentation, Eric. So Mohamed he's a student still, I guess, because
Yes.
in 2022. And so you're asking, are the beacons specifically made for this system? And if it is the case, how is it distributed to boats, aircraft, or people who might need this around the world? I think most people still
Uh,
don't know this. Yeah.
That's a very interesting question. Well, I'll try to be very brief. Yes, they are made specifically for the system indeed. Today, there's for COSPA Sarsat, there are three types of beacons. They are personal beacons, which are called PLBs. There's aviation beacons, which are called ELTs, and there are how to say maritime beacons, which are called EPIRBs. There is a lot of legislation in place that mandates the use of ELTs, for example, for any aircraft that I think is above a certain size. And the same holds true for EPIRBs, which are for maritime use. For personal, the main focus of this, of COSPA SARSAT, is on these two sectors, which is where most of the legislation has been put in place. For personal use, there is no legislation in place, and it is really up to COSPA SARSAT to try to and to, you know, say the European Commission and institutional organizations to publicize this and to try to get the general public on board. But yeah, so that's more or less it.
Thank you, Eric. I hope this answers
Yeah.
your question, Mohamed Amin. And then we have
So,
another. Yes.
no, it's another question. Yeah.
Yeah,
Okay.
we have another question from Frankie that is asking, does this kind of Galileo SAR beacon could have helped the rescue of Singapore flight MH370 that you were mentioning? And does the aircraft B777 have such beacon on board?
Yes, for sure. It could definitely. Of course, the main thing is that at the time of MH370, there were beacon activation was only possible directly from the aircraft. There wasn't a possibility to remote activate the beacon from ground. And because of security issues, the beacon can only be activated and deactivated by a certain number of um, people, and at the time, it was only in the aircraft. So the sort of trust was put in the pilot and the crew, but it could not be remote activated. And this is what exactly we're trying to put in place now with this remote beacon activation, which is really remote from ground to try to activate a beacon that has gone missing. But yes, the B777 aircraft indeed does have such a beacon. It is not yet incorporating the remote beacon activation capability, but we're working very hard on it.
Thank you so much. Like, thank you, awesome. Thank you, Mohamed Ami and Frankie, for your questions. If any of you has other questions, you can, for Eric, you can drop them in the chat, and we can also ask them towards the end if you think of any question. And now, I will then let the floor to Santiago to talk about safety of life service and how it supports civil aviation. Thank you, Eric, again.
All right. Thank you, Melis, for the introduction, and thank you everybody for attending this webinar on the use of Galileo for civil aviation. Can you see my screen, or the you see the full screen, right, Melis?
Yes, but it's not a full screen.
Oh, you see.
We see also your notes.
No
Yes.
problem. Let me just switch, and
Yeah.
that should be fine now, right?
Yes.
Okay,
Yes.
okay.
All good. Yeah.
Perfect.
Perfect.
So then, well, so it's my name is Santiago Perea. I'm together with Melis and Eric. I am part of the Galileo project office here at the European Space Agency. And it's my pleasure to be presenting today the use of Galileo for safety of life applications. Actually, wasn't that long ago that I was at ENAC. That was back in spring this year. We have a working group together between the EU and our American counterparts. You will see why later this presentation. We have a coordination working group, and it was hosted by ENAC. So long time ago, I was there actually working on Galileo safety of life service. So the idea here is I wasn't sure how familiar you guys were going to be with the use of GNSS in aviation, or basically aviation safety in general. So the idea is that I navigate you through these 15-20 minutes. I navigate you a little bit about safety of life applications, which part of the phases of flight are critical, or the so-called safety of life operations in the phases of flight. And that will be an introduction. Also, I will also give you a little bit of an overview of how GNSS is supporting today civil aviation, so systems which are already aircrafts are flying are already incorporating today, and what is the future on how Galileo is going to support civil aviation for the years to come through the two European programs, through EGNOS V3, which is under development right now, and the future horizontal area. So basically, the idea was to introduce what a safety of life operation is, and a safety of life operation in general doesn't have to be something related to civil aviation, but safety of life operation or safety of life criteria is defined when a malfunctioning of the system without the proper warning can derive or can result into three things. Typically, it's death or severe injury to people, loss of serious damage of equipment, and environmental harm. You might have heard before the design assurance level. So typically, we assign the design assurance level when we're designing a system, depending on the criticality, on what a malfunctioning of that system will lead to. So typically, safety of life operations. And in aviation, we have three criticalities: the major, hazardous, and catastrophic. And we see this in not only aviation, but for example, anything related to natural disasters, like a malfunctioning of a nuclear plant or a chemical plant, or even a car crash is part of the safety of life. So this is in our daily life. Train crashes, everything that would imply a malfunction of the system would imply would lead into severe damages. Typically, when I collected these slides, it's good to see when we're flying an aircraft, what is the critical phases of flight. So when most of the incidents or the fatalities occur when we are flying an aircraft. And this was a report collected by and published by Boeing Commercial Aircraft, where they gathered the data between 2008 and 2017, and they put a percentage of the fatal accidents and the onboard fatalities. And then the funny thing here is that, well, there's something too funny, or at least the interesting thing here was that most of the fatalities and most of the critical accidents occurred during the final approach and the landing, as you might imagine. So when we're talking about civil aviation and we're talking about safety critical, we are talking about final approach, so terminal area and landing, which is the most critical part. If some of you are already familiar with civil aviation requirements or ICAO Annex 10, so I'm gonna go briefly through that, so to give you the context. But before giving you the context of the civil aviation, this is regular system engineering. When we are defining a system, we say we have three criteria: the integrity, the continuity, and the accuracy. And the integrity is the measure of the trust that we can put on a system. So basically, I am getting navigation service through GNSS, but how much can I trust this navigation solution, this position solution? So that's the integrity. Then we got the continuity, which is of how often do I get this service interrupted? So how often do I have to abort landing, for example, or how often do I have to abort any operation? This is the continuity. And then the accuracy is the precision that I get in my nominal performance. So all these three things combined is what we define as availability. Is that a system is available when the three criteria are met. And here I put always two plots when the fact that a system is less accurate doesn't mean that it's less integer. So the one that you have below, this system is way more integer than the one above, even though nominally is less accurate. So in civil aviation, we need to do the three things together. So it has to be integer, it has to be continuous, and it has to be accurate. And I define these three things. I define these three things because we're going to talk about different phases of flight and how much Galileo can contribute to different phases of flight. Before going to that, I wanted to take one slide to tell you what is the conventional navigation system that we have today, because you might have seen already that you say, okay, GNSS is relatively new. Civil aviation existed before the implementation of GNSS, before GPS came, before Baidu, GLONASS, Galileo came up. What are we intending to do here? And why are we introducing GNSS navigation, GNSS services into the civil aviation? So I always like to remind people, because you might have seen, everybody has used an aircraft or pretty much nowadays. So you might have seen boxes like this or elements like this very close to an airport, where you have the navigation systems that we have today. So navigation systems that are certified today, and we are using in our aircraft guidance from airport A to airport B. The funny thing about this is that even though we might see aviation as a newly developed or latest technology, technically we're flying today. This is certified and approved by ICAO with systems that were developed in the 50s. Systems that are extremely robust, like the VOR or the DME. So basically, this is a 2D positioning system. The VOR is no more than you have a distance with respect to a vertical localizer and an angle with respect to that vertical localizer, and then you have basically 2 degrees of freedoms in a 2D map. And this is a very old system. It's robust, but it's very inflexible, and it is something that it is end-to-end in the sense that it's one receiver, so it's a one transporter to one receiver back and forth. So basically, it's a bilateral communication, and something very similar happens with the DME. So these two systems, we're not going to enter into how they're done. The funny thing, and I always like to remind people that we are trying to replace things that have been there since the 50s. So even though we think that aviation is always at the very last state of the art technology, this is the civil aviation that we have today, which is certified, and it is applicable today. And GNSS is trying to get into that and make a more robust, more flexible, and more eco-friendly aviation guidance system. So in the in the ICAO PPM manual, when we have the GNSS performance requirements, you might understand that when we are doing when we're flying, so basically when we have continental or oceanic navigation, in which we have several kilometers of protection level, the idea here is that you're more flexible to have uncertainty in your position, or integrity in your position. Integrity is always there, but the uncertainty on how much you can move from, let's say that if we're flying across the ocean and we're flying from the US to Europe, whether I am in a route, I am 20 meters to the left or 20 meters to the right in my lateral navigation, that is not critical, since I have enough space to have some margin in there. But as you might understand, when I'm landing, being 20 meters to the right or 20 meters to the left does have a critical impact. So the criticality of the malfunction is what I bring back with respect to what it was the safety of life operation. The criticality of the malfunction here depends on the phase of flight that you are. And you might imagine that the closer I am to the terminal, and this is what you have in the right, in this plot, in the right part, the closer I am to the terminal, the more restringent my conditions are, because a failure close to the terminal or landing can result into a fatality. Whereas when I have a failure in navigation, I'm not talking about the mechanics of the aircraft, that's a totally different thing. But a failure in navigation while I am flying over Greenland has not the same impact that a failure when I'm approaching Toulouse Airport. And this is going to be important, because when we have the more demanding conditions we have, we will see how much Galileo by itself or Galileo augmented by other systems can support our phase of flight. The important thing here, and this is, I always say the same, that the integrity has to be guaranteed independently on which phase of flight you are. So you have to have the same integrity while you're over the ocean that while you are approaching an airport. The difference is the alert limit, and the alert limit is no more than how much uncertainty, how big the uncertainty area that I have can be. We will go through that now when we talk about protection levels and the fundamental of integrity, the protection level interpretation. So basically, when we talk about protection levels, and this we're gonna go through how the protection levels get reduced depending on the system that we use. When we're talking about protection levels here, it's like, I always like to imagine it as a cylinder in which you say the probability that I get my solution and I have a volume defined by a cylinder, by the protection level in vertical domain and horizontal domain, is that how likely, what is the probability that I am outside this defined volume? And this is the integrity risk. And of course, when you're operating a system, you always have four sections. You can have nominal operation, as you see here. You can have hazardous misleading information, which means I have a failure and I'm compromising the integrity, but I am not warning the user. So that's basically why I'm compromising the integrity. I have a failure and I'm not able to warn the user. Then I can have a false alarm, which is related to continuity. Basically, it's that I'm always interrupting I can be interrupting the system illegitimately. So basically, I have a false alarm, meaning that I am declaring a failure, but actually there's no failure. And then I have the detection case. So we always say that the safest system is the one that never works, obviously, because if I don't allow a system to work and I'm interrupting the system all the time, then I cannot have a fatality. I cannot have an integrity violation of something that never works, right? So that's the fundamental of system integrity. I try to be fast in there because I just wanted to locate you, to put you in the position to understand how GNSS is getting into the game, replacing those systems that were there developed in the 50s, right? So when ICAO introduces these civil aviation requirements, let's look at this from a different perspective. ICAO puts the requirements and say, I'm not forcing you to fulfill these requirements with this navigation system or with this navigation system. I just want you to be compliant. And then how GNSS can fulfill those navigation requirements with the systems that we have today in place or what we are developing, right? So I always like to put this plot, like say, every time I get a position solution, we get our measurements and we locate our aircraft, and then we say, okay, this is the position solution that I get only with the satellite sim view, and then I do my least square estimation, and then basically I come up with a position solution. But what's the problem? This is always in case of nominal behavior. But let's assume that one satellite has a faulty measurement, and then I am computing my solution in an erroneous way. As I said, if I compute this solution in an erroneous way and it places me 20 meters away or 30 meters away from my true position without a warning, while I am flying over Greenland, is not a problem. The problem is when I'm in a terminal area or very close to land. And this is, I always like to mention that erroneous measurements, and this is where Galileo plays a role, and where the GNSS plays a role, is not only that our GNSS systems as of today, both GPS and Galileo, we are extremely accurate. I mean, the systems and both of the systems have enhanced to be very accurate. The systems don't only need to be accurate, but they need to be integer. So in case of something goes wrong, the system has to be enabled with a flagging mechanism or with a notification mechanism to warn the civil aviation users. So what do we have today? Many of the systems might be already familiar to you. So when we have our GNSS, we want to augment it. Augment it means we build an integrity layer on top of it. And then we have two types. As of today, we have two types of augmented. We have the externally augmented and the onboard augmented. And the externally augmented, you might have heard about the ground-based augmentation system. I know my colleagues at ENAC are pretty active on that, or at least they were very active some years ago. Our colleague Christophe Maccabieu, professor at ENAC, they were very active in GNSS integrity, and they were also active in GBAS, in the GBAS working groups. So we have externally augmented systems in which that augmentation doesn't come from the system itself, so it doesn't come from the GNSS. It comes from an additional system that provides this layer of integrity. Typically, is a monitoring concept, is a monitoring system that guarantees the integrity. And this, we can have two types. We can have the local base, so the ground base, which is called the GBAS, or the regional one, which is the space base. The major difference between, we're going to have a couple of slides on them. The major difference between ground base and space base is that the ground is done at airport level. So basically, the warning and the monitoring is done at airport level, whereas the space base is done at regional level. It's more continental. So you have a full coverage area that cover a full system that covers a region of airports, normally above a continent, Europe, America. We will go through that. Some facts about the GNSS today. What do we have today certified? So since 1995, GPS L1 single frequency is certified for RAIN. So sorry, for RAIN. We will go with RAIN, which is receiver autonomous integrity monitoring. WAS, which is the regional American, so it's the space-based, this American ESPAS, is certified since 2003 for LPV200 approaches. That means category 1 approaches. Category 1 approaches, for those of you who are familiar, that means that no visibility up to 200 feet, and from 200 feet on, the pilot has to see the runway. So basically, it's full autonomous navigation, fully trusting the GNSS augmented to 200 feet decision height, and there is where the pilot has to see it. We have today GBAS certified for category 1 operations in certain, I think it's in Frankfurt, Malaga, and several other airports around Europe. And those systems are certified today. So ICAO approved the use of those, and then EASA in Europe and the FAA in the United States approved their use. And one highlight is that as of March this year, 2023, ICAO approved the use of Galileo for civil aviation equally to what it was for GPS in 1995. So GPS was basically approved for civil aviation in 1995, and Galileo, upon its completion, will be is approved already by ICAO for civil aviation use. So any aviation receiver can already incorporate multi-frequency, so dual frequency E1, E5A Galileo. Finally, to talk about the GNSS augmentation system, we have the onboard augmentation system. So that means that the users don't receive anything from outside. So the entire monitoring is done. So the integrity is checked inside the aircraft. And then we have augmented GNSS with EMUs, altimeter sensors, and the most relevant one as of today, with is a hot topic, which is the receiver autonomous integrity monitoring, which is basically the concept of measurement redundancy and integrity check internally. So here, as I was saying before, depending on the phase of flight that you are, we see where each system comes. So today we have GPS and Galileo, both approved by ICAO to do continental and ocean, so continental navigation. That means that when we have alert limits in the order of 185 meters. So an alert limit, as I said, is the cylinder. So we have a cylinder for lateral navigation, so it's a 2D, in which you can have an uncertainty of 185 meters. As you might imagine, this is easier to fulfill than when we are into an auto landing, of course. And then today, SBAS, so EGNOS and WOS, the American one, and the European space segment, space-based augmentation system, they can support category 1 operation. So as I said, LPV200, so full guidance up to 200 feet decision height. And in the future, we have dual frequency, dual constellation GBAS, in which our colleagues, the latest analysis and the latest investigations, they aim to do auto landing Cat 2, Cat 3 GNSS-based operation. So basically zero visibility, which today is only achieved in certain airports if the airport is certified and if the airport is enabled for category 2, 3 through instrumental landing systems. So now, just very few, just only one slide about the GBAS, the ground-based augmentation system. So basically in the GBAS, what we do is that as we said, that we don't trust the constellation by itself, so we need to monitor the constellation. And the ground segment of the GBAS, what it does is basically monitoring that everything is going nominal, that the solution that the user, the aircraft that is about to land, navigating to the airport can be trusted. And that trust, that integrity, is provided by the ground segment located at the airport. So what you will see is that between the major difference between this and the space segment, and the space-based augmentation system that I will provide later, is that the corrections and this monitoring is done in a local level. So for example, in case of the GBAS, is done per airport. So each airport has its own equipment and its own 4 antennas that are monitoring the satellites. And the space base is a regional one, and we'll see how. So basically what we do is that there is a VDV link between the aircraft and the ground is constantly monitoring and sending the aircraft okay, not okay. Basically it's telling the aircraft, you can trust that satellite, or you cannot. And then your solution is integer or not. So basically the receiver, but that's why it's called externally augmented. The receiver has very little integrity allocation. The integrity allocation comes mostly from the monitoring on the ground. For the space segment, for the space-based augmentation system, the concept is exactly the same. You have, instead of having a local monitoring, you have a regional monitoring over America, over Europe, over India, or over Korea. Those are the 4 currently in use augmentation systems, which basically does the same. What we have is a region of a set of receivers in a region that are constantly monitoring the satellites and are providing through a geo. The difference is that in case of a GBAS, the connection is done airport to aircraft, whereas in case of a regional system, is done ground through geostationary satellite to satellite. So the data link is not done from the airport, but from through a geostationary satellite connection. But the concept is the same. So there is a monitoring chain which has to alert the user in case of an anomaly, and the user is notified whether a satellite shall or shall not be included in the position solution. Of course, how this is done in Europe, we have the EGNOS, basically, which is our today EGNOS V2, which is on operation, which is GPS only L1 augmentation system. This is certified today and in operation, covering the entire continental Europe and serving all LPV200 approaches. So as I said, category 1 as of today, and this is an European system owned by the European Commission and procured by ESA and a system designer. So some facts about the EGNOS is basically, as I said, is a network of stations. Today we have 39 stations, and those stations are monitoring the satellite. And then we have 4 mission control centers, and those mission control centers basically and in real time monitoring the satellite and sending messages to the user on whether they shall or shall not use those satellites for integrity. And finally, we have the third one, which is, I said, we have the 2 externally augmented ones, and then we have the internally augmented one. And the internally augmented one, it's basically it's basically a self-consistency check. And the self-consistency check, the concept resides on the fact that you always have more measurements than the strictly needed to compute a solution. So that means that if we go to the basic theory of least square estimator, if I have 4 equations and 4 unknowns, I only have 1 solution. But if I have more equations than that unknowns, I can always do least square estimator and do residual check. So this is the concept of array. The fact that I have more measurements than the strictly needed to compute a solution allows me to do a lot of integrity checks. So basically, today we do something called multiple hypothesis solution separation, which the receiver says, okay, I have, using GPS and Galileo, I have around 13, 14 measurements, but I only need 5 equations. So the rest is what allows me to do subset solution and start checking consistency. If all my measurements are correct, the different subsets of solutions shall be consistent between them. And in case one is non-consistent, then this inconsistency is what triggers the alarm. So basically, the concept of self-integrity, so it is relying on the receiver side to do the consistency check. It is based on the fact that if all the measurements are fault-free, all the solutions should be consistent. And if there is an inconsistency in the solution, that means that there's gotta be something wrong with that particular satellite. But again, the difference between this system and the other system is that the integrity here stays within the receiver and within the aircraft, and the ones coming from ground or space, the integrity is externally provided by a ground segment, basically a ground monitoring network. Today we have the future of GNSS integrity, the one that is not yet in place, is what we call the dual constellation array. So we have our working groups with our counterparts in America, and basically what we are defining is the standards and the receiver standards and the ICAO documentation that enables the use of GPS and Galileo by an aviation receiver, and use this internally augmented system that provides global. This is the difference between the external ones and the external augmented one and this one. This one provided by Galileo and GPS, you have global coverage versus local or regional coverage that you have in the case of GBAS and ESPAS. And this is done everything through the L-band measurements. So basically, the receivers collect GPS and Galileo L-band measurements and receives what the so-called integrity support message. And in this integrity support message, what the receiver does is computing all these checks that I was telling you about, all these solutions of all the multiple hypotheses. So computing a subset, another subset. For this, you need what is called the performance commitment. So basically, a minimum performance commitment that is coming from the system. And this is where Galileo has made a tremendous effort in the past years, up to the point where ICAO has certified us, or well, certification is EASA, but ICAO has enabled the use of Galileo for civil aviation, which is the important part. And now we enter into the Galileo support to HE-RAIM and EGNOS V3 and what we have done. So basically, Galileo being still in initial service, we haven't reached so far, as I think as Miley said at the beginning, we haven't reached so far the FOC, so full operational capability. We're still in initial service. Galileo has shown the ability to support aviation through basically two services. We have the EGNOS V3, which is dual frequency, dual constellation. I said before that the one that we have today in certified and in use is EGNOS augmenting GPS L1 only, so only one band. And then the EGNOS V3 will augment not only EGNOS, but also Galileo in both frequency, the aeronautical bands, so E1, E5, E5A. And for that particular thing, the system, so Galileo system, has to commit to certain performance. And basically the compliance to this performance is what made the over compliance. So basically we are over compliant to this performance is what made Galileo suitable for civil aviation, for EGNOS and for ERA. And I'm going to skip that because I think we're running a little bit late. So I think this is the most important part that I wanted to convey. In November 2023, so in a couple of days, the Amendment 93 to the ICAO Annex 10, which is basically the one that governs navigation for civil aviation, will allow the use of Galileo for civil aviation. So basically, any receiver can incorporate Galileo dual frequency for safety of life applications. And the important thing is that we have not only as a program led by Commission and also with our counterparts from EUSPA, we have not only achieved that this commitment that we're also showing further commitments in other parameters like probability rate of failure that will be incorporated in the future release of ICAO, the ICAO Amendment 90, of the ICAO Annex 10 Amendment 94. So the important thing, as I will show in this slide, is that through our performance, we have warranted, Galileo has warranted robustness for civil aviation use. And what we say in our ICAO SARPs, which is the standard recommended practice, what we say is that those figures of merit that you see here in the slides, those are what we committed as a system to provide. And what you see in the third slide, in the third column, it is the actual characterized performance. As you see in terms of probability of failure, so when you say the SAT and when you see the SAT and the cons, those are probability of failures and probability rate of failures. So the message that I wanted to convey is that we committed to certain magnitudes, as we committed to certain figures of merit that we exceeded by an order of magnitude. So basically, we are one order of magnitude compliant to what we would say, to what we said that we would be. As you can see, for example, in terms of probability of failure, we said we committed to 2 × 10⁻⁵ per hour, and actually what we observed today is 6.2 × 10⁻⁶. Same for single individual satellite faults or for constellation faults. And the important thing is that the compliance to this commitment shows the robustness of the system towards civil aviation, toward ICAO. So this is fully consistent with the material that we provided as a program to ICAO, and ICAO validated for the use of Galileo. The ICAO validated the use of Galileo for civil aviation. So the conclusions, think I'm still on time. The conclusions and what I wanted to convey here is that GNSS provides. So the first part of the talk was about how can GNSS support civil aviation and basically introduce certain gaps or modernize the civil aviation navigation concept as of that we have today, which, as I said before, is coming from technology from the 50s. How can we enhance that to make it more efficient, to optimize airports and civil aviation to be more eco-friendly, to reduce noise and to reduce cost? And basically, we said that as of today, we have an European and an American operational GNSS-based landing system that support up to Cat 1, so LPV 200 approaches. And they're both available in American soil and European soil through EGNOS and WAS. We are under development as ESA, as a system design authority. We are under development on the EGNOS V3, which incorporate not only GPS, but GPS and Galileo dual frequency. And this is done by our colleagues in actually in Toulouse and Munich, Airbus Defense and Space. And also that we have the ground base, which is today presents a promising technology for supporting auto landing. So basically category 2, 3. These were the two externally augmenting, and we have the internally augmented, so the onboard augmenting, which the RAIN offers a favorable alternative towards SBAS, because SBAS is regional only, whereas when we are navigating from one continental area to another continental area where we have coverage of SBAS, in between we have no augmentation system coverage, and ARAIN is global because we don't need a ground segment sending corrections or sending integrity message through a dedicated data link like the VDV link or the geo connection. For that, Galileo basically has shown a strong performance commitment, and Galileo has shown that it can be a robust and an integer system to be supporting civil aviation. And the important thing is that in the future, so today, neither Galileo nor GPS has included this integrity support message that we have defined for the RAIN, for the advanced RAIN, but this will be included in both in INAV for Galileo and in the L-band, in the LNAV for the case of GPS. And this basically will enable to go beyond what we have today for civil aviation supported by the Galileo program and our counterparts in America. And I think that with that, it's a lot of information, but I hope that at least you guys got the basic on how Galileo can be supporting civil aviation. And with this, Melis.
Yeah, thank you so much. Thank you, Sandy. Very, very insightful as well, very interesting. I think we already have a question for you in the chat, actually, so I'm just going to read it straight ahead. And if anyone else has a question, of course, feel free to drop it in the time. So Serge is asking, as civil aviation complies with EASA, FAA, and space complies with ECSS, MTSS, what certification standards was used for Galileo certification? Space 1, Civil Aviation 1, or a new one?
Well, this is an important question. Galileo is endorsed, so ICAO is not the one that certifies. ICAO endorses, and this is important. So I cannot talk about certification standards right now because certification is under EASA and under FAA. So this part is a little bit more controversial. So what I can say, I fully understand the space compliance with a different standard than the aviation. The important thing is that what I can say certainly is that the aviation receivers, so basically the receivers that are going to be tracking Galileo and GPS dual frequency, those receivers are based on the EASA standards, so basically in the ones for Europe and the FAA, and they are coordinated through the RTCA Eurocase. So basically they're following the RTCA Eurocase standards. This we can say. I would not enter into the space certification of the space because we're not certifying the satellites because the satellites have been already launched. Let's put it that way. But what is important is that when we are certifying the receivers are following RTCA, Eurocase, civil aviation standards, which are compliant with the requirements for both FAA and EASA. Not sure if that answers the question.
Yeah, he said, okay, thank you. So I think it does answer the question.
Okay.
Thank you, Santiago. And then we have another question from Hortense asking, what is the integrity commitment for ARAIM today?
So the integrity commitment is the slide that I showed before. So ARAIM today supports lateral navigation. Well, basically, today, as of today, for GPS, supports lateral navigation RMP 0.1. So that means are 300, around 300, so it's 0.1 mile, so 0.3 miles. I think this is in the order of 300 something meters, alert limit. So this is today with what we have with GPS L1 only. When we go to Galileo GPS dual frequency, we still have lateral navigation. So the vertical navigation will not come until we have until we have the vertical range. So we have the vertical range will come. I cannot make any commitment, but let's say that the vertical array is envisioned with the provision of an integrity support message through L-band signals. So today, what we have is a lateral navigation envisioned with GPS and Galileo together. So if you think of the commitment, whether today HARAIM can do what EGNOS does, no, it's a complement, and this is what I was saying. So HARAIM is global, and HARAIM is supposed to bridge the gap that we have between two continentally augmented systems. So basically between, I always put the example between continental US and continental Europe. So when you're going over the Canaries already covered, but when you're going in the middle of the Atlantic, you have no coverage from any of them. So basically it's where HARAIM is providing you for that particular phase of flight integrity that you wouldn't have before HARAIM, until you enter into the two coverage areas of EGNOS or WAS. Hopefully that.
Okay, thank you. She says it answers perfectly, so great. Thank you so much. And then we have another question from Sylvain asking, so you mentioned the possibility of using GPS and Galileo at the same time. Does that mean that it could be the possibility of the same accuracy as EGNOS and replaced it?
Well, there's a major difference between the accuracy, the integrity. It's more comparable, but the accuracy, you're talking about a differential versus an absolute. The differential, so EGNOS is providing correction, so the accuracy of EGNOS is going to be difficult to beat. It's going to be difficult to beat because the key point of the accuracy of EGNOS is that you're sending corrections, so you're basically monitoring. But the accuracy of EGNOS, you only have it over Europe. You don't have it, and this is what I wanted to say. The HARAIM is trying to bridge this gap between the two continents, but certainly the accuracy. But in any case, Galileo per se and GPS per se are accurate enough today. So the accuracy is not we don't have our issue. I said in my presentation, our issue today, Galileo is the most accurate GNSS today. It's even beyond the gold standard that before Galileo was GPS. Today, we managed to have a better accuracy figure than GPS. So Galileo, the position solution provided by Galileo, even if you combine it with GPS, the accuracy of the dual frequency, dual constellation solution is extremely good today. So accuracy is not the key for HARAIM. HARAIM provides integrity without a permanent monitoring network from a regional or local system. But of course, when you have a dedicated network, either GBAS or EGNOS, providing corrections, you have a differential GNSS. Differential GNSS will always provide you better accuracy than the absolute GNSS. This is for sure.
Super, thanks. And he says, yeah, thanks, and that it's an INAC procedure designer question. So thank you so much. Thank you for your questions. If you have more questions, you can ask them also now while we have this exchange with Eric and Santiago. So thank you again, Eric and Santiago. Actually, since they were asking questions to you, Santiago, I'm going to jump straight onto my question that I have for you as well. So you mentioned that in March 2023, Galileo reached a milestone in being accepted for civil aviation by ICAO. So what can we expect Galileo to achieve another milestone in the future with respect to the level of performance for ICAO SARPs? And also, will other constellations benefit from this improvement?
Yeah, but that's a very good question. So basically, we envision the reduction of this performance commitment. So today, as I showed before, we committed to certain performance level, but we are overperforming by an order of magnitude. So as the constellation matures, as our monitoring matures, and we have more confidence, we will be able for sure to reduce this performance commitment. So we foresee in the future as a program to go to ICAO and being able to demonstrate that we can reduce this performance commitment. So basically, we can enhance the performance commitment. And the thing is that the more you reduce your performance commitment, the better protection levels you can get. Basically, so basically, this cylinder that I was talking about, it gets smaller and smaller, and you can operate as I think Hortense was asking. The future of ARAIN is vertical ARAIN, and vertical ARAIN needs more stringent commitments from the constellation, and neither GPS nor Galileo were there yet, not yet, but it is the future of ARAIN. It is moving towards lateral, not only lateral, but also vertical navigation, targeting Cat1 operations. So certainly we will hopefully get there by enhancing our performance commitments.
Okay, super. And so can these improvements also support other constellations other than Galileo?
Well, at the end, we're in a globalized world, and civil aviation uses multi-constellation. So I wouldn't say that this enhances other constellations. Basically, this enhances the performance of the end user, which also use other constellations, but the other constellations per se might not get benefited. We might get maybe motivated by the good performance of Galileo to enhance their systems. That could be a possibility.
Okay, thank you so much, Santiago. A follow-up question from Frederic Arnold saying, so considering that aircraft operations are done today with GPS N1 only, and it works quite well, what would be, according to you, the main operational benefit visible for airlines in using Galileo for civil aviation?
That's a very good question. That is a very good question. Well, basically, today we have only coverage with GPS L1, but we don't have any coverage. Basically, as I said before, we cannot do lateral navigation, or at least not to the level where we want it in the continental area without the inclusion of Galileo and GPS dual frequency. So basically, we will be able to support in the future. So the continental navigation outside the regional coverage of EGNOS or WAS, and the additional constellation and the additional frequencies will enhance in the future, or will allow us in the future to go beyond Cat1. So today it works well with Cat1, but we are aiming to move beyond Cat1 with GNSS. And of course, the receiver, we're not talking about one receiver for ARAIN, one receiver for EGNOS. It's a multi-frequency, it's a dual frequency multi-constellation receiver for both.
Super, thank you so much. I hope this answers the question, your question, Frederic. So, okay, another question from Frankie, and then we can move to the exchange, and you can continue asking your questions, and we can move them towards the end. But so Frankie is asking, do all Airbus and Boeing aircraft are equipped with satellite communication equipment to manage both GPS and Galileo signals? And the other one is, or do some aircraft need some retrofits to manage Galileo?
That's a very good question, because Galileo wasn't endorsed by ICAO until this year. The receivers were not yet basically standardized. So right now, together with our colleagues from EUSPA and together with our colleagues from the entire community of the RTCA and EUROCAE, we are developing. We're very close to finish the MOPS for the dual frequencies of the Galileo GPS dual frequency multi-constellation receivers. And today we don't have a manufacturer. So the manufacturers are obviously in the loop, as everywhere they are in the RTCA and EUROCAE. Today, not certified receiver is handling Galileo, because Galileo was not endorsed by ICAO until this year. But as of now, once the receiver standards have been finalized, together with the aviation community and the aviation receiver community, those receivers will be able to be manufactured, and those receivers will be incorporated in the aircraft. And of course, the second question, some retrofits to manage Galileo, I think that answers the question.
Thank you. Thank you so much, Santiago. Okay, now, so continuing in this exchange, I will ask a question to Eric now. So yeah, if you can, you're joining us back. So basically, so
Yeah,
you mentioned,
I'm here.
yeah. So from what you presented, SAR, well, Search and Rescue is clearly a special Galileo service because compared to others, it is part of this big COSPA-SARSAT program. And so I was wondering, does this bring particularly any constraints at system design level in terms of the SAR payload development, but also SAR message formats? And how are these constraints discussed and decided at an international level with ESA and with other stakeholders?
Okay, very interesting. Very interesting question, Mylis. Thank you. Well, for sure, it brings a lot of constraints. The first of which being you cannot do what you want, or only what you want. So it is very interesting. COSPA SARSAT is a big organization which gathers several participating states, has four founding members, which kind of direct the direction that um, the program is going, and that puts a lot of constraints of what we can do in terms of designing either payloads or ground systems. In counterpart, of course, this brings interoperability between the systems. So you have to, from the get-go, put that into your design, which means that you don't have that much flexibility. You have to account also for what others are doing. You have to account also for backwards compatibility, meaning that you cannot just decide to throw away a whole system and put in place something newer, better, that performs better, but you have to account for other members that might not want to update their systems, that are happy with how the system performs today. And so all of these things have to be taken into account into your design, into your operations, and everything you do with respect to your own contribution to the system. So this to make this work, COSPA SARSAT is sort of organized as a big standardization body. You might have heard of other standardization bodies like ETSI or 3GPP. That standardize ground communications. So the same happens in COSPA SARSAT. It's a big standardization body which has regular meetings where people discuss either programmatic or technical matters. Sometimes the technical discussions are how to say tempered by political directions that one member wants to take or another, or by constraints that one member states wants to put on the system or not. And this makes it very interesting, but it's all very sort of structured in this in a hierarchical, it's a very difficult word in English to say, hierarchical way, in which you have all the four founding members, France, Canada, the US, and Russia, that have the power to decide or to sort of endorse whatever technical decision has been taken, and to dictate which technical aspects of the system will be worked on in the next few months or even years. And then technical groups organize themselves at a lower level. They do all the technical work in the standardization sort of framework where different member states and organizations put in their contributions. These are discussed in regular meetings, like either online or in person, depending on the sensitivity of the topic. And yeah, as I said, these take place regularly, and then they're reported back to the higher entities, which then endorse it or put their stamp of approval or block it. And then the system advances like that. So it makes for kind of slow progress. You might see it like that, but at the same time, it makes for a very resilient system, that very robust, where everybody has a say of point of entry and has also their say with their contribution. So I hope
Super.
that
Very,
answers more or less.
yeah. Yes, that is it perfectly. Thank you so much, Eric.
All right.
Now I had another question more to the both of you, just to talk about other services as well. So you have presented two services that can support civil aviation, one for integrity for navigation users and one for emergencies and rescue operations. So when GNSS is used for such a critical sector as civil aviation, we also always want to think, well, we are first sometimes to think about targets, threats targeting the sectors, like spoofing particularly. So the fact of sending fake or modified GNSS signals to make the user think he's in a certain place or in a certain position where he's not. So for the spoofing particularly, are there any Galileo services today that can help mitigate these spoofing attacks, these threats?
Yeah.
I don't know,
Santi, would you
Eric
like
or
to?
Santiago, if you want to.
Yeah, well, I can tell you, I can give you a corporate answer from ISA. I'm not an expert on OSNMA. So we're talking about the open service authentication. So basically, Galileo is providing a service as part of the portfolio of the multiple services Galileo is provided, in which we have an authentication of the navigation message and authentication of the signal. As part of that authentication of the message, for example, Eric might be able to answer for EWS, but I can tell you that as the integrity support message, which is this new message that will provide beyond, so more capabilities in the beyond what we have today in HRM. This is part of the OS authentication. So basically, this is we have an extra layer of protection in the open service and also in the integrity. But of course, the cyber attack, well, the spoofing is always a very controversial topic, because it in a chaotic world as we have unfortunately today, attacks, especially cyber attacks, are sadly a trending topic. But Galileo has already on top of it has already a protection layer that might help, might improve this anti-spoofing attack. But again, and the OS authentication is something that is beyond my let's say my competences here at ESA. But we have excellent engineers that you might want to invite for giving a talk on Galileo authentication.
For sure, we will invite it next time. Thank you, Eric. I don't know if you want to complement Santiago's answer or.
Yeah, sure. I can complement a little bit, because actually, on the services I look after here at ESA, which are SAR, as you might have guessed from my presentation. I also have another hat, which is the emergency warning service hat. And both of these services are intended to also be authenticated with the same method of OS navigation message authentication that Galileo provides. Without going into the details of the service as such, I think what we need to know is that it's just a service that will, or a set of messages that will authenticate or prove with a certain reliability that a message actually comes from Galileo. For search and rescue and beacon command service in particular, this is very relevant. Not so much for the activation of the beacon, because if an aircraft is, say, an aircraft is in normal operations and somebody wants to spoof an activation of the beacon, there is no real harm done, right? Because they can very quickly contact the pilot and prove that, well, actually, no, this is not a real emergency. The problem for beacon command service is for the deactivation of the beacon, which is much more critical, because if you actually have a sort of malicious disappearance of an aircraft and you want to activate a beacon, you want to prevent that this beacon is also maliciously deactivated. And therefore, it is of crucial importance that for this particular use case, the messages are authenticated. For the emergency warning service in comparison, let's say, it's another service that we provide, which is for the people in France. You might be sort of aware of the FR alert, I think, that has been recently been put in place, which is a method of letting people know through their smartphones that there is some sort of, it's a notification um, service through ground infrastructure to let you know via your smartphone that something is going on around you. That can be anything from a thunderstorm coming or a tsunami if, say, you are in Cyprus or something like that. And with Galileo, we're also looking to provide a complementary system for when ground infrastructure is down to also be able to alert people to their smartphones using the Galileo satellites. And here again, if you are in a situation where there's chaos ensuing everywhere, you want to make sure that malicious agents are not taking advantage of this by giving false information to users. So it is again of crucial importance that messages that come from Galileo alerting the general population are authenticated. And why this is even more important than in ground infrastructure is because we have to remember that each Galileo satellite has um, has a visibility of 1/3 of the Earth. So if there is something happening, that you have a very large coverage via satellite that you can alert the population from. So yeah, so just to answer the question, yes, there is something in place, and you will see it more and more in, I guess, in the public domain as we declare these services and the adjacent authentication service is put in place, supporting service.
Super. Thank you so much, Santiago and Eric, for the answer. Now I will go more into, let's say, lighter questions or more open questions to you two, and I will after that
I
also
think we
address
have
the
a
question.
question, Maëlys.
Yeah. Okay, you want to address it now? Sure. So Frankie is asking, does Galileo provide specific services to military armies, like a location more precise, inferior to 1 meter?
Well, this is what we can tell you is that Galileo has a public regulated service, which is for member states with functional
Governmental use.
for governmental use. Unfortunately, there's not much more we can disclose in an open forum
Yes.
due to classification issues, as you might understand. But yeah, there is a dedicated service for governmental use for the member states. But that's for sure.
Yeah. And if you want to find out more about the applications, you can look it up on the internet. You can have some examples as well of governmental applications of a
It was
PRS.
very interesting. I think over a year ago, I read it was in the news, so it's public information. The local police in Berlin, so they implemented with the PRS receivers, so the public regulated service receivers. They implemented an application and a service in there. They did not say that much, but basically what they mention is that the police cars in Berliner Polizei they were incorporating PRS receivers as a baseline. So I think this is excellent news.
Yeah.
Unfortunately, we're not we cannot talk much more in an open forum about this.
Yeah, but thank you for asking the question. It is indeed a good question. Okay, so jumping into the more later questions, and I'm surprised we didn't have any question on the equations from Santiago, that no one wants to tackle this topic. So for the open questions, yeah, just talking about your career at ESA and also on the services Sol and on your side XR in AWS, I had just a questions to start with is what is your best memory or anecdote since working on your respective Galileo services? I hope they are good ones. I hope they are good memories.
Yeah. Well, the day to day is pretty intense. Okay, this is a good difficult question. Okay, I don't know about one specific good memory. What I can say is that I really enjoy as we've been discussing, Galileo and SAR Galileo in particular is very exposed to outside interaction with different member states, with different, we also have our colleagues from the European Commission, from the European Union Agency for the Space Program, EUSPA. In SAR, we interact with CNES quite a bit. I have to interact a lot with COSPA-SARSAT members. And that is something that, although it is not easy every day because there's hard technical discussions, I thoroughly enjoy. I think it's extremely enriching to be able to see how different organizations work, how different people interact. So we have a lot of interactions with, for example, the Americans from NOAA who look after SAR GPS, and they have a completely different way of working, and we can really take a lot from them. That, you know, that's for good memories I have. And we have several meetings. Sometimes we have to move to another place to discuss these things in close confined quarters. And you know, at in the moment, this is not always very nice. It's very tiring, but afterwards we always laugh about it. But now I was speaking, one thing that came to mind about the memory. I don't know if it's a good one or not, but not very long ago, I got a call at sort of 2 a.m. in the morning from the Coast Guard here, because we do very regular tests for our return link service using our test beacons here. And of course, the Coast Guard here in the Netherlands has my number. And so sometimes they give me a call to see if we're doing a test, and I got a call at 2 a.m. So I was completely knocked out sleeping from the Coast Guard, asking me if I was doing a test. And then, yeah, so then I had to, at 2 a.m., turn on my computer, have a look of what we were doing, half asleep. So it was, yeah, it's one of the quirks of of working in SAR. You have to be available 24/7. But so that's it on my side. Maybe Santi
Thank
has
you.
better
Yeah, very,
anecdotes. He's been working on this for very long.
yeah.
Well, not at ESA though. Before that, I was working at industry side. So, and before that in a research institute at DLR, the German Space Center. So, one of the things is that I think I have a pretty good overview of the, let's say, research or research institute, industry, and ESA. And I pretty much enjoy the ESA position. ESA, one of the cool thing about ESA is that we are the system designers. So we actually are hands-on together with our industry partners. So we design the system. We also look at the anomalies of the system. So one of the things that I enjoy the most, even though it's always stressful when you have anomalies in the system, tracing the anomalies, fixing the anomalies, understanding why the system behaved that way. There's always sort of like this investigation, this it is also the novelty of it's a living system, and you get the capability to improve it, at least in G1, and then lesson learns from G1. We're moving to G2, and this history that we've been having over the years about the things that could have been done better, and we can implement that. One of the things that I do also like a lot about working at ESA is that, as Eric said, we do interface with a lot of people. So we have like a dual phase. We have an institutional phase in which we also interface. In my case, for example, we interface with the FAA and with Commission and with our American counterparts to define this global system. So that's also very enriching because you see other ways of working. You talk to the GPS colleagues. You see how the DoD does it. The approach from Galileo coming from civil. Galileo is a civil. It's mostly civil. It's a civil system designed by ESA and funded by the European Commission, versus GPS was intentionally made for military and the civil aviation. So basically, the civil service is a byproduct of a military system. I think this is a major difference that you see when you interact with the Americans, that they have a totally different way of working, a totally different way of scoping their system. Is one of the things that I like the most. And about I'm thinking about memories. I think every day, I mean, people might not think, I mean, besides the weather, which is pretty bad in the Netherlands, is something that you might not enjoy. But apart from that, the day-to-day work at ESA is really nice. We have a very nice working environment. People are very open, very technical. It's very easy to exchange. Sometimes you can get caught up in discussions for long, designing down to the message, down to the bit level. So even though people might think that this gets very institutional, it's not that institutional. That basically, we do a lot of technical things here, and I think this is what I like the most. And I was thinking, one of the things that I like the most is when we are doing when we're deploying new racks, for example, in our lab, and when we are deploying the new. Recently, we got a demonstrator. I think like 6 months ago, we got a demonstrator from an H2020 activity, actually for the rain. So there's where you start. So you go to an acceptance review. You start witnessing the test. You have to accept the machine. So basically, it's when you see that there is a realization of something physical that you have been working with industry, and then deliver the rack, and then you start say, oh yeah, this is what we did, what we designed, or this is, and then you see the product, the final product. I think this is every time there is a deployment of physical hardware here at ESTEC is also really nice.
Just
Really
one
great.
thing.
Yeah.
Just one thing to say, a good memory comes from this morning. My Elise, unfortunately, you're not here, so you missed it. But a colleague of ours brought a big stack of crêpes.
Yeah, I saw the email. I wasn't there. I thought, yeah, I'm
Yeah,
remote.
You missed it, my
see,
lead.
I missed the
it's
clip.
that's a good
Well,
recent
that's true.
memory.
There is always, I don't know how, but in this department, there is always either cake, chocolates, something in the kitchen. There is always something in the kitchen.
And that's what we will remember.
And good to work
Amazing.
with you.
Thank you. Yeah. Yes, we had someone speaking.
No, good to work with you, I said.
Ah, yes, exactly. So as we only have a few minutes left, I'm checking if there is any more question in the chat. Otherwise, I have a last one. But if people on the chat want to ask more questions, there is a few more minutes left. Okay. While we wait, I just had maybe one last question. Let's say, because we also have students joining us now, so maybe a bit of career advice. Let's say. So my question would be: could you give 3 words to describe your career so far, and also what word of advice would you give to young professionals listening to you today? Tricky question, I know, but
Santi, would you like to go first?
How my career, I would say intense, with no breaks in between. So I would always advise that once you're done with college with the master, try to take like a 2, 3, 5 weeks break. But that's aside. But I think, as I said before, one of the things that I like the most about my career is that I've been in research, industry, and ESA. So I think when you're at ESA, or when you're an institution, you also, it's good to have the industry perspective. So you see, because at the end of the day, ESA is the designer, but industry is our hands. So I think being in the industry, being in case space, which is what I know. I don't know automotive, unfortunately. But Eric has way more experience than me outside space. I've been doing space since I left university. But I think seeing different things. Seeing industry, then maybe research. So you might think that that sticking to one single position forever, it's good, or one path in one company. I've been in different places, and I think that's been really enriching. And changing is always good. And you might not change, not because you're every time I changed from DLR to Airbus, Airbus to ESA, wasn't because I was unhappy at all. That's what makes even the decision more difficult, because I was really happy in the 3 places, but I thought it was time for a change. So change is good. I would say that changing different perspective, changing, even though I didn't change the topic, but I've changed the perspective, and this is always good.
great. Thank you so much for your answer. Eric?
Um, okay, so I tried to answer in 2 parts. So you asked for 3 words. I don't know how to put it in 3 words. I can put it in 4. I would say all over the place in terms of my career, because and just to amplify a little bit what Santi was saying about change. So me personally, I've been all over. I've also started in academia, then I went to industry. I never really looked at space as one of the possibilities, because I'm an electronics engineer, not specifically a space engineer, but um, I always went towards something that I liked, and this is just maybe the only piece of advice, if this can be called like that, um, to the younger generation, let's say. is that don't hesitate really to stick your neck out and try something new if you so fancy. You know, it's not because you have studied one particular thing, if you're a specialist in civil aviation, that you cannot just say, you know what, I really like where the telecoms industry is going, and I want to go in that direction. And sometimes, yeah, it feels a little bit uncomfortable. It takes time, you know, to ramp up the knowledge. It really gets you out of your comfort zone. You might face some rejection. I can speak from experience. I was rejected many times from ISA before being able to join. Um, you know, but it's just not to get discouraged. Just insist, and really, I can say it's definitely worth it, if only to learn something new. You know, for me, that's the message. Just keep on trying.
And
So
something
that's it.
that I would add on top of it, I think Eric has mastered that, living in different countries. So the Netherlands is my fourth country. I think Eric has way more experience in living in different countries than I have. But I've moved 4 times, 4 countries, and this also has been very enriching. And one of the things that I like the most about engineering is that we're so versatile. You don't have to stick to one topic. I mean, all the skills that you learn in one job might be, you might know the technical knowledge for that, but all the extracurricular skills, which are not related to the topic, the ability to think, the reaction, all this kind of this engineering thinking, way of thinking, I think it's transversal. And space was always my topic, but it could have been structural engineering. I have an aerospace engineering background, and I only specialize in navigation at the very last part of my master's. I always thought I was going to be doing aerodynamics and fluid dynamics, and I ended up in navigation. So I think we're engineers the way we are educated in college, and also the education you get after college at work is transversal. You can go to automotive, space, telecom. I think it's as Eric said, don't be afraid of change. I think this is my advice. Change.
Great, thank you so much. So the final word: embrace change, get out of your comfort zone. We have a question. Okay. No, just saying thank you for the presentation and for the organization. Super. So if we don't have any more questions in the chat, yeah. So the final word of advice: embrace change, get out of your comfort zone, stay curious, and keep your hopes up, I would say. But overall, I just want to say thank you so much, Santiago and Eric, for joining us today for the webinar. I think it was very enriching for people with a civil aviation background to learn how Galileo can support the field. And also a big shout out to Estelle for helping me with the organization and of course doing everything perfectly as always. But yeah, again, thank you so much to our guests and to the audience. And so this will be uploaded on the YouTube platform of ENAC Alumni, and we can also share the slides potentially afterwards. But thank you all so much, and have a great evening.
Of course. Thank you very much
Thank
for
you.
organizing.
Thank you, Eric. Thank
Bye.
you, Santiago.
Thank you.
Goodbye.
Thank you for having us.
Bye.
Bye bye.